Let us begin today's lecture, and today's lecture is about the next type of full wave rectifier, that is called as bridge rectifier. So bridge rectifier is nothing but it is a full wave rectifier. Now again I will be following the same strategy. First of all, introduction, then construction, then working, after working waveforms, then analysis. So by the same strategy we will be studying the bridge wave rectifier. So let's start with the introduction. Here 4 diodes will be used. See, in half wave rectifier only one diode was used. In full wave rectifier, center tapped, 2 diodes were used, and in bridge wave rectifier we use 4 diodes, 4 different diodes. Now for positive half cycle 2 diodes will be utilized, and for negative half cycle remaining 2 diodes will be utilized, and therefore we can say that both the half cycles will be utilized, and that's why it is called as full wave, because in both the half cycles the diodes are in forward bias. Okay, we will draw the diagram and see that. So I will be writing it here, the introduction. It consists of bridge of 4 PN junction diodes which work in both the half cycles of input wave, and hence, because both the half cycles are being utilized of input, and hence its efficiency is similar to that of center tap full wave rectifier. So efficiency will be same, that is 81.05 that we have seen in the last lecture. Now let us go for the construction part. The second part we will be studying, that is so this was our first part, and the second part is construction. Now for that purpose I will be drawing the diagram. So let us draw that. So we will be having, of course, our source of AC power supply, which is a step down transformer. So I will write it here, 230 volt 50 hertz AC supply, which is input. And now I will be having a bridge. So let me draw the bridge here. So intentionally let us mark 4 points, and now these 4 points will form a bridge. So I will be starting with the first diode. So let me draw the first diode. Then I will be drawing the second diode, so they will be merging into each other, remember this. Then I will be drawing the third diode. So third diode will be coming to this point like this, and then I will be drawing the fourth one. So these 2 points are marked. Okay, now let us connect it. So this point, the first point, I am just joining to this, means the secondary, the first point of the secondary, let us call it as M. I am calling it as point M, and then we will be dividing the points. Okay, so it is MN, then diode D1, then you will be having a resistor RL across which the output will be taken, and that is connected to this point. Remember this. Okay, and the second point is then connected to this point. So this is the diagram for bridge rectifier. So I am talking about the point. So it is, let us say, M, N, O, then it will come to this point P, Q, R. So I have given it the name. Let us say it starts from M to N, diode D1, then this is diode D2, this is diode D3, this is diode D4. Okay, so what will happen? See this point M, N, O through resistance P, Q, R. The point will be, the current will be flowing from positive point to negative point. And in the reverse, the opposite will happen, means it will start from R to D2 to resistance to P to D4, and then it will be out. Okay, we'll see that in the working part. So what is the construction part? It consists of, first step down transformer through which the AC power supply will be applied, then 4 PN junction diodes, then the third one, load resistor RL, across which the output is taken. Okay, now let us see the working of this. So I will be, of course, writing the next point, which is our working. So working of bridge rectifier. So I will be in need of this diagram. I hope the diagram is clear. So let us see here. So again I will be considering 2 points. The first is positive half cycle, and the next point is negative half cycle. So when we apply positive and negative half cycles, I can draw it here. This is, let us say, this is the input waveform that I can apply. So it consists of positive half cycle and negative half cycle. So when positive half cycle is applied, point, say this, point M becomes positive and point R becomes negative, because you are applying a positive half cycle. So point M will be positive and point R will be negative. Because of point M positive, now point N will be positive. Once point N is positive, this diode will be in forward bias because its anode is at higher potential with respect to cathode. See this, the path is M, N, diode D1 forward bias, through load resistance, it will come to point P, from P, then diode D3 will be in forward bias, then Q, and then to the negative, because current flows from higher potential to lower potential, so it will be completing its path. So how the current is going to flow? Remember this, when the positive half cycle is applied, then the current will flow through the path M, N, O, load resistance, P, Q, R. And what are the two resistors which what are the two diodes which are in forward bias? The forward bias diodes are D1 and D3, while diode D2 and D4 will be reverse bias. These are going to be forward bias, and diode D2 and D4 will be in reverse bias, and hence you will be getting a positive half cycle. You will be getting a positive cycle because of D1 and D3, because they are in forward bias. In negative half cycle, the opposite will occur. Now what will happen? The point R will be positive and point M will be negative. See what will happen this, because of this point R positive, point Q will be positive, D2 will be positive, means forward bias. O, load resistance to P, from P to D4, and from D4 to, then we will be going to N, and then the path will be completed when we will be reaching N. So exactly opposite path. So here what will happen, the current will flow from R to Q to P, see this, R to Q to O, R, Q, O, load resistance, P, N, M. Okay, and now the diodes which will be in forward bias will be D2 and D4, while D1 and D3 will be reverse bias. So here again you will be getting a positive half cycle, and that will be because of D2 and D4. That will be because of D2 and D4. Okay, so again see this, when you apply positive half cycle, point M becomes positive, point R becomes negative. The current will flow from M to N to O to load resistance to P to Q to R. Now you will say, sir, when the point is coming like this, point M to N to O to load resistance to P, then why it is not going towards N? Remember, this point is positive and the current flows from higher potential to lower potential. That's why it will not be moving through it, but it will be coming down and going to R. Okay, I guess it is clear now. See this, point M is positive, N is positive, O is positive, P is positive, Q is positive, R is negative. So it will be completing its path from higher potential to lower potential, and the same case will happen when negative half cycle is applied. Okay, now let us move ahead and see the waveforms of this circuit. So now I will be trying the waveforms. Okay, again I will be drawing the input and output waveform. So this is your input voltage, omega t. This will be my output voltage, so I am writing it V0 and omega t. Let us draw the input waveform. Okay, sinusoidal wave, 0 to pi to 2 pi, 3 pi, 4 pi, 5 pi, and so on. I'm just taking those points down so that I can draw the proportionate diagram. Let us draw the output in blue color. So for positive half cycle, diode D1 and D3 will be forward bias. So you will be getting a positive half cycle because of D1, D3. Then again a positive half cycle, then again a positive half cycle, again a positive half cycle, again a positive half cycle. So you will be getting only positive half cycles, but the cause of those positive half cycles will be different diodes, like D1, D3 for positive half cycle, D2, D4 for negative half cycle, again D1, D3 for positive, D2, D4 for negative, D1, D3, and so on. So this is what you will be getting. So you will be getting all positive half cycles, and all the entire full wave of the input waveform is being utilized by the rectifier to give the output, and hence we can say that its efficiency is good. All the 4 diodes are working to give you the output. Okay, now let us we have seen the things. Now remember the analysis, the next part is analysis, and the analysis of center tapped full wave rectifier and bridge is same. What is the meaning of this? The values are going to be same, like the value of VDC will be similar to that, so twice Vm by pi. The value of IDC will be twice Im by pi. Vrms will be Vm by root 2. Irms will be Im by root 2, so we need not to analyze that. Then PDC we can calculate similarly, so it is going to be 4 Vm Im upon pi square. Then PAC is going to be Vm Im upon 2. Then efficiency 81.05. Then ripple factor 0.48. Same TUF, same, that is 0.636. Okay, then percentage regulation is going to be same, form factor is going to be same, form factor. Then peak factor is going to be same. Only thing is that will be different is PIV, the peak inverse voltage. Why, I will tell you. Now what is peak inverse voltage? Peak inverse voltage is nothing but it is the maximum voltage that you can apply when the diode is in the reverse bias. See here, when you apply positive half cycle, diode D1 and D3 are in forward bias, while diode D2 and D4 are in reverse bias. Similarly, when you apply negative half cycle, D2, D4 becomes forward bias and D1, D3 becomes reverse bias. So this is forward bias, this is reverse bias, this is forward bias, this is reverse bias. Now the total voltage applied at this point is Vm, and total voltage applied at this point is Vm. So you are applying Vm plus Vm, means you are applying twice Vm, but this twice Vm is being divided into 4 parts, because we are having how many diodes? 2 diodes in positive half cycle, 2 diodes in negative half cycle, which are reverse bias. Okay, so total diode is 4, so that twice Vm is going to divide, it is getting divided into 4, that is Vm by 2, and therefore remember this, the value of peak inverse voltage for individual diode is Vm by 2. But remember, for every half cycle, 2 diodes are in reverse bias. So it will be Vm by 2 plus Vm by 2, so it is going to be Vm. It is going to be Vm. So Vm for positive half cycle and Vm for negative half cycle. So that's why PIV, the maximum in reverse bias voltage that we can apply to the diode is Vm. That is Vm. Remember this. It is not twice Vm as we have seen it in the center tap full wave rectifier. Okay. Now next important question that we will be discussing here, that is most probably asked in the examination. So I am writing it here, important. Important with 3 stars. Compare half wave rectifier, center tap full wave rectifier and bridge rectifier. And they give certain points on the basis of which you need to compare. Remember this, when I compare, I don't only write the differences, I write the similarities as well as differences, because it is comparison, it is not that differentiation between the 3. They are asking comparison, so there can be similar points, there can be the difference point also. So now what I will be doing, I will be dividing this page into 4 parts. The first part I will be writing is parameter, on the basis of which I will be comparing the rectifiers, then half wave rectifier, then center tap full wave rectifier, then bridge rectifier. Remember, in examination don't write the table kind of thing, but try to write in paragraphs, like the first point is this, and therefore in half wave rectifier we will get this, in full wave rectifier will be getting this, and bridge rectifier will be getting this. Okay, so let us write the first parameter. So first parameter is circuit arrangement, how the circuit will be there. So I will be drawing it in brief. So this is going to be V0, this is RL, this is D1, 230 volt, 50 hertz AC supply. Okay, here what will happen, again you will be having a step down transformer, but now we will be using two diodes, and those two diodes will be center tapped. The load resistance is going to center tap the input waveform, and the bridge rectifier we have just drawn. So you will be having 4 points. So this is going to be a diode number D1, this is D2, D3 and D4. Then you will be connecting it. Okay, so it is going to be through load resistance that I will be connecting, and then we'll be connecting it like this, the load resistance to it, and this point to this. So this is the diagrammatic arrangement that we have already seen, so we can refer to the previous videos. The second point is number of diodes used. So here it is going to be 1, here 2, here 4. Third, DC voltage. So what is the value of DC voltage here? So here VDC is Vm by pi, here twice Vm by pi, here also twice Vm by pi. Then DC current, next parameter, IDC is going to be Im by pi, twice Im by pi, twice Im by pi. Fifth, RMS voltage. So Vrms is equal to Vm by 2, Vm by root 2, Vm by root 2. Then RMS current, IRMS is equal to Im by 2, Im by root 2, Im by root 2. All these values we have derived, okay. Then PDC, then 8th one, PAC, then 9th one, percentage efficiency. So it is going to be 41.05, 40.05, 81.05, 81.05. Okay, then 10th is a ripple factor, so it is going to be 1.21, 0.48, 0.48. And the 11th point is TUF. So here the value of TUF comes out to be 0.286, here it comes out to be 0.636, and here it will come out to be 0.810. Why? Because the secondary will not be divided, so exactly whatever is the efficiency will be appearing as a TUF, transformer utilization factor. Then we have the point called as PIV, so it will be Vm, twice Vm, again Vm. Then you can write about form factor, you can write about peak factor, you can write about percentage regulation. So this will be a very important question as far as your examination is concerned. Remember this is going to be very important 7 marks question. Mark this as a important question, 7 marks. Okay. Now let us take some numericals based on full wave rectifier and bridge rectifier, of course. Okay, so let us start with the numerical. So I will be writing the first numerical. Okay, a full wave rectifier supplies load of 1 kilo ohm the AC voltage applied to the diodes is 220-0 220 volts RMS. If the diode resistance is neglected, calculate first part average voltage, second part average current, third part ripple voltage, fourth part ripple factor. So these are the four things that are asked. First of all, let us try to understand what is numerical. So I will be writing the given part first. So let us say the load resistance is RL is equal to 1 kilo ohm, which is given. See, the load is of 1 kilo ohm. The AC voltage applied to the diodes is 220-0 220. What is the meaning of that? The meaning of that, it is center tapped rectifier. The secondary is divided into two parts. So one half is getting 220, another half is getting 220, and this middle value is 0. That is the meaning of this thing, and it is RMS value. Okay, so secondary RMS voltage 220 is given. Okay, now the diode resistance is neglected. That means RF is equal to 0. Calculate average voltage means VDC, average current means IDC, ripple voltage means VR, and ripple factor means R. These are the four things that we need to calculate. Okay, let us calculate that. So first of all, the RMS voltage of secondary of transformer is Vrms, which is given by Vm by root 2. Therefore, peak voltage Vm is equal to root 2 multiplied by Vrms, and that Vrms value is given how much? 220 volts. It is given as 220 volts. Remember this. So let us calculate the value of Vm from there. So it is root 2 multiplied by 220. So let us calculate that. So it will be root 2 multiplied by 220, and the value comes out to be 311.12 volt. So we have calculated the peak voltage Vm. Now we need to calculate what? We need to calculate VDC. So we'll write for center tap full wave rectifier, VDC is equal to twice Vm by pi. So twice multiplied by 311.12 divided by pi. So let us have this value, 311.12 multiplied by 2. Okay, and that divided by pi, and therefore the answer comes out to be 198.06 volt. 198.06 volt. Let us calculate IDC. So I will write DC current. IDC is equal to VDC upon RF plus RL. So it is going to be 198.06 divided by RF is 0 and RL is 1 kilo ohm. So 1 into 10 to the power minus 3, and that will give me the value 0.198 ampere. 0.198 ampere. Okay, then they have asked you to calculate a ripple voltage VR, which is under root of Vrms square minus VDC square. Vrms, you know, it is 220. So 220 square minus 198.06 square. Let us calculate that. So it is under root of 220 square minus 198.06 square. Yeah. So it comes out to be 95.77 volts. Now I know that if the numerical needs to be correct, the value of a ripple factor will come out to be 0.48 because it is a constant value for the full wave rectifier. So let us check it. So ripple factor, the last thing that we need to calculate here. So ripple factor will be VR upon VDC. So VR comes out to be 95.77 divided by 198.06. Let us calculate that. So it is 95.77 divided by 198.06, and the value comes out to be, it comes out to be 0.48. It comes out to be 0.48. So our problem is correct. So remember, they don't ask many values. They ask only 3 or 4 values, and that can be asked for 8 marks or it can be asked for 7 marks. So depends on how many means parameters are asked. The marks depends. Okay, but let us solve it for everything. Okay, from next numerical, what we will be doing is we will be solving it for everything, so that what will happen, our practice will be there for each and every parameter. Means if they ask some parameters, we will be okay with that. So any parameter if it is asked, we will be having a practice of solving the numerical. So next problem we'll be taking, and in that I will be calculating every value. Okay, but remember, in the examination they will not be asking you each and every value. They will be asking any 3 or 4 values, and that you need to solve. Okay, so let us start with the second problem. Okay, a full wave rectifier uses a load of 1500 ohm with no filter. Assume each diode to have idealized characteristics with RF is equal to 10 ohm and RR, reverse resistance, infinite. Sine wave is applied to the diode having amplitude 30 volts. Calculate first peak DC Rms voltage and current. Second, DC power. Third, AC power. Fourth, percentage efficiency. Fifth is a ripple factor. So these many values we need to calculate. Okay, so first of all let us write what is given. So that given part will clear many things in our mind. So let us calculate or let us write given. So extract some information from this. A full wave rectifier uses a load of 1500 ohm. So I will write RL is equal to 1500 ohm. No filter is used. Of course we have not used any filter here. Assume each diode to be having idealized characteristics with RF is equal to 10 ohm. So RF value is 10 ohm for each diode. Okay, 2 diodes are there because it is a full wave rectifier. RR is infinity, no use. Sine wave is applied to the diode having amplitude of 30 volts. What is the meaning of that? The meaning of that is Vm is equal to 30 volts, because if I write the equation for sinusoidal wave, it is Vm sine omega t, where Vm is nothing but it is the amplitude of the wave. So Vm is equal to 30 volt. Now on the basis of this we need to solve the problems. Okay, so let us start with voltage. So peak voltage is given. So similarly I will write, so peak voltage Vm is equal to 30 volt. I have calculated first value. So what will be the DC voltage? So DC voltage VDC is equal to twice Vm by pi. So 2 into 30 by pi. So let us calculate that. 60 divided by pi. So it is 19.09 volt. 19.09 volt. Okay. Let us calculate now RMS voltage Vrms. So it is Vm by root 2. So it is 30 by root 2. Let us calculate that. 30 divided by root 2. So it is 21.21 volts. It is 21.21 volts. Okay. So these are the 3 values we have calculated. Let us calculate current from there. So I will write peak current Im is equal to Vm upon Rf plus RL. So Vm is how much? 30 divided by the value of Rf is 10 given, and then 1500 is like this. So 30 divided by 1510. So it is 19.86 milliampere. 19.86 milliampere. Let us calculate DC current. IDC is equal to twice Im by pi, so it will be twice multiplied by 19.86 into 10 to the power minus 3 divided by pi. So let us go for that. 2 multiplied by 19.86 multiplied by 10 to the power minus 3, whatever value we are getting, divided by pi. So it is 12.64 milliampere. 12.64 milliampere. Let us calculate RMS current IRMS. So it is going to be Im by root 2. So it is 19.86 into 10 to the power minus 3 divided by root 2. Let us calculate that. 19.86 into 10 to the power minus 3 divided by root 2. So it is 14.04 milliampere. So we have calculated all the 6 values. So first part of the problem is over. That is peak DC and RMS voltage and current. Now it is saying that we need to calculate DC power and AC power and efficiency. So let us calculate DC power first. So DC power PDC is equal to VDC into IDC. It is, what is the value of VDC? Let us put the value. So the value of EDC is 19.09, and the value of IDC is 12.64 into 10 to the power minus 3. So let us calculate that. So it is 19.09 multiplied by 12.64 into 10 to the power minus 3. Yes. And you will be getting the answer, that is 241.29 milliwatt. Okay, similarly I will be calculating AC power PAC, which is Vrms multiplied by IRMS. So Vrms is 21.21 and IRMS is 14.04 into 10 to the power minus 3. So let us calculate that. 21.21 multiplied by 14.04 into 10 to the power minus 3. So it comes out to be 297.78 milliwatt. Now we'll go in for percentage efficiency. So it is PDC upon PAC into 100. Output upon input multiplied by 100. So output is 241.29 milliwatts. That's why 10 to the power minus 3. 297.78 into 10 to the power minus 3 into 100. This 10 to the power minus 3, 10 to the power minus 3 get cancelled. So it is 241.29 divided by 297.78. Okay, multiplied by 100. So it is 81.02. 81.02%. 81.02% is the answer, which is of course which is similar to the analysis value that we got. So our numerical is going fine till now. Next value that we need to calculate is a ripple factor. So let us calculate ripple factor. So we'll write a ripple factor R is equal to under root of Vrms upon Vdc whole square minus 1. So I know what should be the value. The answer is coming out to be 0.48. Let us check it. So Vrms, I will put the value Vrms. So Vrms is 21.21 divided by Vdc is 19.09 square minus 1. So let us put it. So in root we're having two values, 21.21 square divided by 19.09 square entire minus 1. Okay, it comes out to be 0.48. It comes out to be 0.48, which marks that the numerical is correct. Okay, let's take the next numerical, the third one, the last for full wave rectifier. So I will not be taking any numerical on bridge. Those numericals are same. Okay. So in center tap full wave rectifier, RL is equal to 1 kilo ohm, RF is equal to 10 ohm, full stop. Primary voltage applied to step down transformer is 800 sin omega t with transformer turn ratio 2. Stop. Find average current. B part is RMS current, C part is ripple factor, and D part is percentage efficiency. Okay, so let us extract some information from the problem. So it is a center tap full wave rectifier with load resistance 1K, forward resistance 10 ohm. The primary voltage applied to the step down transformer is 800 sin omega t. So it is VI. So write VI is equal to 800 sin omega t. With the transformer turn ratio means small n is equal to 2, and that is step down transformer, so the value is going to be half. Okay, so I will be just, other information is not given, so let us start with the problem. So we will write the RMS voltage of secondary of transformer is nothing but is N2 by N1, which is a turn ratio, which is opposite of turn ratio, multiplied by VI. So it will be 1 by 2 multiplied by 800, so it is 400 volt. It is 400 volt. So voltage available at the primary of the transformer is 400, but because it is center tapped, alright, because of center tapping, Vrms will be Vrms by 2. Why? Because half will be available to first part and half will be available to the second part. Okay, so from there we are going to calculate now. Therefore I will write peak voltage Vm is equal to root 2 multiplied by Vrms. So root 2 multiplied by 200. So let us calculate that. So I will write root 2 multiplied by 200, and that comes out to be 282.84 volts. 282.84 volts. Now Vm is available, so let us calculate Im, peak current. So peak current Im is equal to Vm upon Rf plus RL. So it is 282.84 divided by RF value is 10 and it is 1000, 1K. So let us calculate that, divided by 1010. So it comes out to be 280.04 milliampere. 280.04 milliampere peak current. Okay, now let us calculate the next value, that is DC current. So we write DC current IDC is equal to twice Im by pi. So twice multiplied by 280.04 into 10 to the power minus 3 divided by pi. So what will be the value? So value comes out to be 2 multiplied by 280.04 into 10 to the power minus 3 divided by pi. So the answer comes out to be 178.27 milliampere. Let us calculate RMS current. IRMS. So it can be calculated by Im by root 2. So 280.04 into 10 to the power minus 3 divided by root 2. So let me calculate that. 280.04 into 10 to the power minus 3 into 2. Oh, sorry. Divided by root 2. Okay, so it comes out to be 198.01 volt. 198.01 volt. Now let me calculate the value of PDC. We know that the value of PDC is VDC into IDC, but let me calculate it by I square R, because power is also given by the formula I square R. So I will write IDC square multiplied by R, so it is Rf plus RL. So IDC is 178.27 into 10 to the power minus 3 squared multiplied by 1010. So let us calculate that. 178.27 into 10 to the power minus 3 square multiplied by 1010. So it comes out to be 32.09 watt. 32.09 watt. And let me calculate PAC. So it is IRMS square multiplied by RF plus RL. So IRMS is 198.01. Okay, it should be ampere. milliampere. 198.01 10 to the power minus 3 square multiplied by 1010, so it comes out to be 39.60. So it comes out to be 198.01 10 to the power minus 3 square multiplied by 1010. It comes out to be 39.60 watt. Okay, so let us calculate percentage efficiency now. It is PDC upon PAC into 100. So it is 32.09 divided by 39.60 multiplied by 100. Let us calculate that. 32.09. Okay. 32.09 divided by 39.60 multiplied by 100. Yeah, it is 81.03%. So it is correct. Last part that we need to calculate is ripple factor. So let us calculate ripple factor. So ripple factor small r is equal to under root of, now I am calculating it in terms of current because I know the values of current. So it will be Irms square, Irms upon IDC whole square minus 1. I know the value is coming out to be 0.48, but let us check it. So what is Irms? Irms is 198.01 into 10 to the power minus 3 square, and this is 178.27 into 10 to the power minus 3 square. So I have just put the values. So under root of let me put the value 198.01 into 10 to the power minus 3 square divided by 178.27 into the power minus 3 square minus 1. So it comes out to be 0.48. It comes out to be 0.48, and that marks that our numerical is correctly solved, because remember, for half wave rectifier the ripple factor should always come out to be 1.21, and for full wave rectifier the ripple factor should come out to be 0.48. If it is not coming out to be this, you can consider that your numerical is wrong. So this is the end of the second part of unit number 1. We'll be starting with the filter in the next lecture. Thank you.